Good day to you, everyone. My name is Maxime Chambonneau, working at the Institute of Applied Physics in Jena, Germany. And today I'm going to talk about semiconductor metal ultrafast laser welding with relocated filaments. So first, let us introduce the context. So, joining materials is essential for the industry, especially when you want to fabricate complex devices. To do so, traditional methods can be used. Those methods include adhesive bonding, brazing, anodic bonding, and so on. However, those methods show important drawbacks. For instance, such a traditional method may require another material or pressure assistance, or maybe the joint materials may show some aging or degazing problems, or maybe it will not be resistant enough to high temperatures. As an alternative technique, the laser welding technique has been developed recently. Laser welding consists in energy deposition at the interface and provides a fast, clean, and contactless way to join materials. This technique has been shown to be applicable in different material configurations such as glass-glass, as you can see here, glass semiconductor, glass metal, polymer-polymer, and more recently ceramic-ceramic. However, in the case of semiconductor and metal, there is nothing too convincing so far. So why? Let us have a try together if you don't mind. To do so, we will illustrate semiconductor metal ultrafast laser welding with silicon and copper. We will also employ the following arrangement. It relies basically on 9.8 picosecond laser pulses at 1.55 micron wavelength. One can note that at this wavelength, silicon is highly transparent, meaning that we can reach the interface between the two materials. Then, the input pulse energy is controlled by means of a half-wave plate and a polarizer before the beam is focused to the samples by an objective lens. Besides, we also have a microscope working in reflection and in dark field, relying on the same objective lens, a tube lens, and a CMOS camera. Thanks to this microscope, we can image the entrance surface of the silicon sample, and by doing a damage scan on this surface, one can position the geometrical focus with respect to the samples. We also evaluate the bonding quality by post-mortem separation of the two samples by means of an indenter connected to a force gauge. So let's have a first try. Let us set the input pulse energy at 300 nanojoules, and we can measure a shear joining strength of 30 kilopascal. All right. But then what if we double the energy? So for an input pulse energy of 600 nanojoules, the shear joining strength is 10 kilopascals. All right, so the main question here is it sufficient? I mean, can we say that silicon is welded, is joined on copper? Sadly, the answer is no. And actually, in this case, the samples are easily separable by hands. And typical values for other material configurations or traditional bonding methods are on the order of 1 to 20 megapascal. So the main question here is why? To answer this question, one has to keep in mind that silicon is a highly nonlinear propagation medium. Specifically, when one takes a look at the nonlinear refractive index of silicon, it is 100 times higher than the one of fused silica, for instance, meaning that self-focusing will occur at relatively modest peak powers. Let me give you an example. Let us consider an input pulse energy of 1 microjoule, which is pretty typical for laser processing applications. Then the power will be higher than the critical power for pulse durations below 20 picoseconds, which is extremely large. As a consequence, there is a competition between Kerr effect on the one hand and plasma formation together with defocusing on the other hand. In other words, a filament is formed and there is energy delocalization. Two consequences of this. First, there is a saturation of the intensity below the breakdown threshold of the material, as you can see here. In other words, increasing the input pulse energy will not lead to an increase in the laser fluence. Second, there is a nonlinear focal shift. As you can see here, the more the energy, the more the focus is shifted upstream the laser. And taken together, those two consequences lead to a strong depletion of the energy deposition at the interface. So here are the solutions we propose. First, in the frame of laser welding, we will deal with an interface with a metal, meaning that there is increased absorption, which is kind of good. And second, we will relocate filaments at the interface in order to maximize the intensity at the interface. But to do so, we need nonlinear propagation imaging. And this is exactly what we did. We imaged the nonlinear propagation inside crystalline silicon by means of the following arrangement depicted here, which is nothing else than an inverted microscope enabling us to image the back surface of the silicon sample. And then by moving the focusing objective lens here, one can reconstruct the 3D fluence distribution inside silicon for different input pulse energies. And thus, one can access to the nonlinear focal shift delta Z as a function of the input energy. On the data here, three regimes are exhibited. First, for extremely low pulse energies, lower than 10 nanojoules, the propagation is basically linear, as confirmed by point spread function analysis that we carried out thanks to our in-house tool, which will be released soon. This is called InFocus. In the case of intermediate energies, so between 10 nanojoules and 100 nanojoules, one can see that the focus is unambiguously shifted upstream the laser, but the shape is overall conserved. Finally, in the case of extremely high input pulse energy, one can see that we reach the filamentation regime, as you can see here, with multiple focal positions. So to conclude on this data, one can see that increasing the input pulse energy leads to an energy deposition which will be far from the interface. In order to predict the behavior of the nonlinear focal shift as a function of the input pulse energy, we have developed a semi-analytical model. This model relies on this equation here, where delta Z corresponds to the nonlinear focal shift, F star corresponds to the sample thickness, and ZNL, NL for nonlinear, corresponds to the effective focal length associated with Kerr effect, which is considered as a lens. Then one can determine the value of ZNL by using Marburger formula, which is shown here, where K0 is the wave number, A0 is the beam radius at the entrance surface, PCR is the critical power for self-focusing, which is a first fitting parameter, and P is the reduced peak power at the exit surface, which is defined as follows. Here we have taken into account the 2-photon absorption during the propagation in silicon for estimating the reduced peak power, and P0 represents the input power, and beta 2 star corresponds to the 2-photon absorption coefficient defined for a power. And this is our second fitting parameter. And by means of this 2-parameter fit, we can simulate the nonlinear focal shift as a function of the input pulse energy, as you can see here. And well, the trends are correctly reproduced, meaning that we correctly describe the major physical mechanisms that are responsible for the nonlinear focal shift. Moreover, we have carried out additional nonlinear propagation measurements for shorter pulses, so 860 femtosecond, depicted here on this figure in blue, and well, the results are the same. I mean, the trend is well reproduced, which benchmarks our approach. Alright, so now that we know the value of delta Z for different input pulse energies, we can come back to our initial welding problem. Especially, we can precompensate the position of the focusing objective lens during the welding by delta Z at the desired input pulse energy. And the results are essentially shown here in terms of shear joining strength for two different input pulse energies, without in red and with in green delta Z precompensation. And what one can conclude from this figure is that precompensating the nonlinear focal shift leads to a much better welding. Okay, so now what if we increase the input pulse energy but keep this delta Z precompensation strategy? Well, the results are essentially shown here in terms of shear joining strength as a function of the input pulse energy, and we can reach around 2.2 megapascal shear joining strength, around 1 microjoule, which is quite okay for applications. And this is explainable by the fact that both the maximum fluence and the energy reaching the interface are increased when you precompensate delta Z. Noteworthy, there is no welding possible when the input pulse energy is lower than 100 nanojoules here, which means that silicon copper ultrafast laser welding is solely achievable in the filamentation regime. Ultimately, in order to know more about the fundamental mechanisms involved during the welding, we have carried out material analyses of the welds. First, we have taken some scanning electron microscopy images of the copper and the silicon sample. Concerning the copper sample, we have noticed that some silicon is still stuck to copper even after breakage, which may indicate the creation of covalent bonds. Concerning the silicon sample, we have noticed the creation of nanostructures between the lines, which correspond to the irradiation of the laser. And this may indicate some plasmonic effects taking place during the laser-matter interaction. Concerning the Raman spectroscopy measurements we have carried out, first on the copper, we have noticed a shift in the silicon peak, which may be related to strained silicon. And finally, concerning the Raman spectroscopy on the silicon sample, there is a broadening of the Raman spectrum, as you can see here in red, which may indicate a partial amorphization. One may note that even if during the nonlinear propagation imaging there is no damage formed, here silicon is modified during the welding. And this may originate from an enhancement of the absorption due to the free electrons in copper. and also a possible field enhancement due to the air gap, so a Fabry-Perot cavity. To summarize, we have characterized the nonlinear propagation inside silicon for picosecond laser pulses. By precompensating the nonlinear focal shift, we have achieved the first semiconductor metal ultrafast laser welding. We have obtained megapascal shear joining strength that are compatible with applications. And to go further, we would like to try other configurations like silicon-silicon. We also would like to evaluate the role of the air gap at the interface. And finally, we will carry out a parameter study as a function of the pulse duration, the wavelength, and so on. Finally, if you would like to have more details about the whole procedure, please feel free to scan this QR code here. And this will lead you to our recently published paper in Laser and Photonics Reviews. Also, if you need more information, please feel free to contact me anytime at the following address. And I would like to thank you for your attention.